Right then, good afternoon, everyone. Welcome to the start of the BizCom talk. Right, so the agenda for this talk is do a quick introduction, talk about SmartLoader, about LuaJIT, a bit of the reversing, and then looking forward from the research that we've done, what we can do going forward. And all questions will be at the end. So, introduce myself. I'm Dave Elliot. I'm from the UK. Long 13-hour flight to get here. I'm the principal content engineer at Security Blue Team. I create training materials and labs for teaching anyone to become a DFIR specialist or SOC analysts. In my past, I've had about 10 years of experience in cybersecurity, working across offensive and defensive roles. So, to start, we're going to talk about the SmartLoader malware. So it is a dropper or loader. It's based on LuaJIT, and it's heavily obfuscated. We found the campaign whilst looking for the FortiGate Belson leaks. So to start off, we need to talk about how the SmartLoader works. So it's a bit of malware which is used in campaigns to load further malware onto a system. So, for example, the initial entry vector for a campaign. So, in this one, it uses LuaJIT, which is an interpreted language. Sorry, guys. LuaJIT, which is used for this malware variant, is a custom version of Lua, which supports multiple extra things. So when the language is interpreted, it's compiled down to machine code for faster execution, and it also, within the LuaJIT library, it has the foreign function interface, and in this campaign, it allows it to not only deal with functions within Lua itself, is able to reach out and use the Windows API and do extra functionality, which is heavily used within this campaign. So the LuaJIT interpreter is packaged as an executable with an accompanying DLL, and depending on what campaign it is, or what version of LuaJIT you use, it changes the dialect of Lua that it interprets for you. So let's start talking about SmartLoader. So SmartLoader as a malware campaign is always an archive. So it'd be a zip file, a RAR file, or a tar.gz. So within the archive, it's packaged with a precompiled version of Lua, or the LuaJIT interpreter. It has a Lua library, which is Lua 5.1, and it has the malicious code, which is described as conf.txt within the archive. The user is intended to run it using a runme.bat file, which will then execute the conf.txt using the Lua interpreter. So the way it's delivered is a Trojan-style delivery. So a lot of what you can find with the campaigns is just an example from VirusTotal. Is a lot of the campaigns are designed around game hacks or pirated softwares or key generators, and they're there to get someone to download it and execute it. And so the first attempt at reversing that we did manual parsing of all the base 64. We were trying to drop strings out of the Lua interpreter itself. So we were using debuggers. We were recompiling LuaJIT in order to get the strings before the garbage collector gets rid of the strings. Just everything we can in order to get the strings in a format that allows us to do further analysis. We also did dynamic analysis. So whilst we're running the malware, we're able to see what actions it takes on the system and what things we can do to detect it. So with our analysis, we managed to find out the full execution pipeline. So the threat actor uploads SmartLoader to GitHub. The user downloads, executes it, and the first stage that happens is it will take a screenshot of the user's desktop and do a bit of initial reconnaissance on the victim's computer. Once it's got that, it encrypts a packet and sends that information to a C2 server on the internet with the campaign ID. The C2 server then returns with the next tasks that it needs the user to, the malware to do. And depending on what task that is, it might be to just silently persist on the system and wait for further commands, or it might be to initiate the next bit of the campaign. So on R1, we managed to find that it had, it drops a ransomware binary at the end. So whilst doing our reverse engineering, we managed to find the original obfuscator, which is Prometheus Lua. We've managed to decrypt the C2 communications. We've created a Wireshark dissector for that, and we've managed to simulate the C2 server and infrastructure. The reason why we were able to do that is in order to increase coverage on our dynamic analysis, we were limited by what the C2 servers returned as valid commands. So by breaking the encrypted communications between the malware and the C2 server, we're able to modify which tasks were given back to the malware and adjust the coverage within our dynamic analysis. We've also identified IOCs. So within each campaign of SmartLoader, there's a integer, which is then base 64, and this is the campaign ID. And this is added on to different actions that it takes on the system, such as the scheduled tasks or any caches of C2 commands held on the system. So we can use this campaign ID and the IOCs to track it across the system. So that was all very good, and it took about a week of reverse engineering to get to that point. But we need to be able to go faster and be able to find unique IOCs faster than a week every time. So the first place we looked was the Prometheus Lua obfuscator. So this is a very strange origins. There's a mysterious author that's got no connection with cybersecurity or even just IT in general. It came out of nowhere, making the obfuscator with some connection to Roblox scripts to protect them. He's unknowingly caused headaches to malware reverse engineers worldwide, and this obfuscator is used in multiple Lua-based malware campaigns, such as SmartLoader and Sunseed. So within Prometheus itself, what happens is it passes the entirety of the input malware into an abstract syntax tree. And anyone in here that doesn't know what that is, it's essentially, it breaks down the source code into logical components. Say, for example, if you want to add two numbers together, it will store each number as an individual node on the tree and the function of add. It mixes them all together into a tree-like structure, and that makes it easier for things like compilers and things to be able to make optimization decisions. But in this, what it does is it takes the tree, for example, with the add function, and then adds extra nodes in to be able to make the code execution a bit more obfuscated. So once it's gone through, passed it into an abstract syntax tree, there's a pipeline of multiple stages which do individual modifications to the syntax tree. So, for example, we've got, I'll do that on the next page. So with the pipeline, there's a configuration for the pipeline in itself. So we can choose the Lua version. So for this malware campaign, it was Lua 5.1. But it also supports Luau, which is a different dialect of Lua. You can change the name mangling techniques. So when you have variables within the malware, instead of it being called X and Y, it can be mangled into multiple different names. And then there's a JSON blob for the steps and configurations for each step within. So, so these are the specific modifications to the AST as it goes through. So we've got about 10 different obfuscation steps that it can take. So we've got one for adding variable arguments. So if you've got a function that takes 2 inputs, it will modify that to take up to 50 different inputs, and being able to pick out which one is the correct input for the function itself is very difficult. We've got anti-tamper, that notes down the individual lines that each code element should be on within the execution, and then it has code that checks at multiple points that the lines that the code is on match where it's being defined. So say, for example, you've got a print statement on line 7. Later on in the code, it will look for the print statement and double check that it's still on that line. We've got constant array, so all possible variables and assignments within the script, all of the constants are moved away into a big blob at the start of the code, and then any strings and other variables are then base64 encoded, and then at runtime they are then indexed from the individual blob. We've also got encrypted strings, which are encrypted at obfuscation time and then decrypted at runtime. Numbers to expressions, so static numbers such as like 1024, those are then split into mathematical expressions such as 512 plus 512 instead of the full 1024. Proxify locals, this is a step which moves the variable definitions and makes it an indirect access to the variable when it's declared. It also has steps to split strings, and it has a watermark generator. So it will put, similar to like a stack canary, it will put individual definitions throughout the code and make sure it matches at runtime. And then an easy one is wrapping function, that exactly what it says on the tin. The whole code is then put inside a function statement. The one I've left till last is VMify. And this is an abstract machine which is added on top of the original code. So using the AST, the obfuscator is able to work out the execution pipeline for the original code. And in doing so, it gives a pseudo instruction counter and then loads the code. It shuffles the code and gives it a pseudo instruction counter, and then uses that in a very big switch statement to choose which commands it does at runtime. So it's very difficult to undo the individual command. So we had to find a way of reversing that the SmartLoader way. So what we did was we took the AST interpreter from SmartLoader itself, and we developed new pipelines in order to undo each individual obfuscation step within the code. So progress so far, we've got base64 undone, very easy. The encryption, so we managed to find individual constants within the code, obfuscated code, and able to decrypt it and spit back the original. We can unshuffle all the blob data. We've already got the C2 communication decrypted. We can now modify the payloads from the C2 servers. So essentially, we have control over SmartLoader itself. So if we need to use that to make training materials, we can take SmartLoader with the IOCs and everything associated with that, but run it in a safe way. And also, we have a Wireshark dissector for the C2 communications. So to break the encryption, there are 4 base values within the code, and they follow a very specific pattern of steps. So by taking the constants out of the main blob, we're able to find the patterns in the abstract syntax tree to be able to then get the encryption keys, which are the 4 values, and then pass it all back into the unencrypted strings. Then once we've done that, so the easiest way to do that is by taking the AST, passing it back to Lua, finding the patterns, and then decrypting it, and then putting it back into the AST to be able to do the next steps in the pipeline. So we need to talk more about VMify now. So it is an interpreter within an interpreter. It converts the Lua code into a mixed set of instructions, and then using the pseudo instruction pointer, as discussed earlier, is able to go through in a unique way through the code that's been decompiled. And it's a unique VM for each invocation of the Prometheus obfuscator. So every time it's ran, using some seed values, it's able to make a different VM for each obfuscation attempt. So what you can do to find SmartLoader on your network, we've got Wireshark detectors, snort rules on our GitHub, and file signatures. You can block the Lua binary for this campaign, but they can just repackage it, and they'll be back on your network. And we have blog posts and a GitHub for any further details. So things to do from here. We need to talk about our findings. That's what I'm here for. Is anyone in the room a student at the moment doing a master's? If not, okay, cool. Maybe someone at a later date, but the VMify code still needs to be reverse engineered, and that I estimate to be well over 100 hours worth of work just to do the untangling of it from the AST perspective, and then just polishing off the documentation for the code now. So, key takeaways for the talk. You can use AST to reverse malware. VMify is very hard to undo. We've got a Wireshark detector, so you can see this on the networks. And we've developed a decryption tool. Fantastic. That's the end of my talk. And has anyone got any questions? Yeah. Oh, yeah, no problem. Yep.
Given the work and effort that you guys have done on this so far, is SBT going to start offering reversing certifications or training?
We already have malware reverse engineering as part of the BTL2 syllabus.
But is it going to be expanded out further than just like a module?
I think it's too early to say on that one, but it is something we have been looking into. Any other questions? Yep.
Does your guys' BTLO labs have a challenge that is similar to this?
What, using SmartLoader? We haven't published it yet, but we have got more than one in the pipeline for that. Fantastic. Right, no more questions. Thank you very much.